In this first video in section 11.3, we're going to introduce inverse variation. And let's just start with question number 1. It says you're going to drive to a city that's 72 miles away. And I've drawn a little figure here. So we're leaving Spokane, driving to some city, say 72 miles away. Here's our little baby carriage looking car. And our job in part A is to complete the table to the right. So we're given some various speeds. Our job is to find the travel time, and again here the thing to keep in mind is that the distance we're traveling is fixed. So the key here is the following relationship, right? That we can relate distance to speed and time through the equation distance equals speed times time. So for example, if I was driving 60 miles an hour for 2 hours, 60 times 2 would be 120 miles of distance. Okay, so here, right, the distance on the left is fixed. I'm going to try out a couple different speeds, and I want to know the travel time. So that suggests rearranging things, right? So distance is 72, right? I'm going to go ahead and divide the speed over, and I'm going to solve that for time, okay? So to fill out my table now, all I'm going to do, right, to find the travel time is just take 72, and I'm going to divide it by whatever my chosen speed is. So here, if I was going, say, 40 miles per hour for the entire drive, that would give me a travel time of 1.8 hours. And then if it was, say, 50 miles per hour, that would give me a travel time of 1.44 hours. 72 divided by 60 is 1.2 hours. And then finally, 72 divided by 80 is 0.9 hours. Okay, so we can see as our speed increases, well, it's not going to take us as long to get there, right? Our time is going down. And that brings us to this next part, B, fill in the blanks. Well, as speed increases, travel time, as we just said, this decreases, okay? As speed decreases now, so in other words, if I choose a slower speed, well, that's going to take us longer, right? So here, travel time would increase. For the next part, if the speed were to double, travel time does what? Well, if I say double my speed from 40 miles per hour up to 80, I can see my travel time is going to be halved, right? It takes me half as long to get there. So travel time is halved here. And then if speed were halved on the other side, so if I went from 80 down to 40, of course that's then going to take me twice as long. So here travel time would double. And then finally it says the product of the speed and the travel time is blank. Well, if I basically just do the reverse of what I did to fill out the table, so multiply now 40 and 1.8, I'm just going to get that distance of 72. And I'm going to get that same constant here for every one of these speed time pairs. So 50 times 1.44 is 72. 60 times 1.2 is, well, 72. And 80 times 0.9 is also 72. And for emphasis here, I'm going to say this is 72 miles, right? That is just our distance here. All right. So now moving on to part C, it says since the product of speed and travel time is constant, we're going to say that these two variables are inversely proportional. Write an equation that relates the speed and the time and draw its graph. Alright, so I've gone ahead and I have drawn the graph down here. I've just plotted the data points from the table. And notice here, I'm going to go ahead and label the speed x. Right, this would be the independent variable, and the time as y. So we're saying the time y depends on speed, right, the x value here. So this is on the horizontal axis there for speed, and time is on the vertical axis. And we'll just immediately observe, right, this is not a linear relationship, right? Our data points do not fall on a straight line, okay? Now, also with this labeling of speed is x and time is y, I can rewrite this equation as y equals 72 divided by x, and that's exactly what I've just included down here next to the graph. Okay, so that would be part C. And then moving on to part D, it says, is this a linear relationship? Explain. Well, the answer there is immediately no, right? And that's because we're seeing a non-linear graph. All right. And so moving on to E, it says, if the speed were 0 miles per hour, what would be the resulting travel time? Explain, right? Well, this almost kind of sounds like a joke. What we're saying here is that if the speed were 0, well, in terms of the equation, that's saying that x would be 0. And so what would be the resulting travel time? Well, if I just go ahead and try to plug 0 into my equation, I would get that y was equal to 72 divided by 0, which of course is not defined. Okay, or put a slightly different way, right, in sort of plainer language, if your speed is 0, you're not moving, right? So the resulting travel time would be what? Well, you're never going to get there. So in some regard, it doesn't even make sense to ask what the travel time is. Okay. However, in chapter 12, instead of, say, looking at a speed of exactly 0, we're going to look at something like, let's say, a little snail wants to move from Spokane to the city. And it's moving not 0 miles per hour, but really, 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 really slowly, like close to 0, say 0.01 miles per hour. Well, if I plug in a really small number here for x, 72 divided by a small number is going to give us something infinitely large. Okay, so it's going to take a snail an infinitely longer time to get to the city as opposed to the car. We can also see that, by the way, in the graph. If I make x really small and move to the left, then y, the travel time, is going to get infinitely big. Okay. All right, so then moving on to F, is there any speed that would result in a travel time of 0 hours for the 72-mile drive? Okay, so again here we're saying now something sounds a little bit preposterous, right? Travel time of 0 hours. So this would be saying y is 0, and then we're asking, is there any speed? So x here is the unknown. Okay. Well, this would be like saying, you know, is it possible to somehow like teleport from Spokane to the city? And the answer there is no. Now on the graph, right, we're be looking at something like, well, notice this y value is never going to hit 0. I could make my speed infinitely large, right? Go really, really fast, say approach the speed of light, but while the travel time is going to get really, really small, right? I'm going to get there really quickly. It's never going to be exactly 0 here. So the answer there would be no. All right, great. So now let's go ahead and define what we're going to call inverse variation a little bit more generally. So here I have, for inverse variation, y and x vary inversely if their product is constant. Okay, so just like in question number 1, okay, we saw that the speed x times the time, right, was always 72 miles per hour. Okay, so more generally we're going to say y and x vary inversely if x times y is always some fixed value k, and we'll still call that k the constant variation. Okay, now rearranging this equation, I can also write that as y equals k divided by x. And this is a typical graph when you're working with inverse variation. Okay, and we'll point out here that here as x, say, gets larger, now, unlike what we saw with direct variation, right, instead of y getting larger, y is going to get smaller. Okay, and then likewise, if I made x smaller, so move to the left, y is going to get larger. All right, that's a good place to stop.